Thank you to the ACS Energy and Fuels Division, and thanks everyone for tuning in on this Friday evening. I hope wherever you're calling in from, I hope you're doing well. I know this is such a strange year, and I hope that this will be a nice scientific break from a lot of the craziness going on out in the world. Like Professor Liu said, my presentation today is going to focus on electrochemistry and confinement and layered materials. And first I wanted to highlight that this research was done first by a team from my group, graduate students, Shelby Boyd, who recently defended her Ph.D., James Mitchell, Mike Spencer, and John Wang, Postdoctoral Fellows, Elisa Patterson and Simon Fleischman, and then a series of our collaborators that came from a number of different places, including many of them at Oak Ridge National Lab, who we collaborate through an EFRC on fluid interface reaction structures and transport. And like was mentioned earlier, our work is supported by both the National Science Foundation and the Department of Energy, and we're very grateful for the support, as well as the Sloan Foundation. And we are active users of several facilities, user facilities from the Department of Energy as well. So a little bit of an overview of our research group. We do material synthesis, so we make pretty much all the materials that you see in this presentation, we make ourselves. We also then think about how to assemble those materials into electrode architectures, and that includes advanced architectures for things like lithium-ion energy storage. This is a topic that I will not touch upon today, but I just wanted to highlight that we have this, this endeavor. And then I think one of the things that brings everything together for us is to understand electrochemical mechanisms at interfaces, and utilizing a variety of in situ and operando techniques. These techniques are done primarily through students in my group, but very actively with collaborators like Mike Toney and Nina Balke and so on. So we're very grateful for them and always look forward to working with others in all of these areas. So first I wanted to highlight that the work in our group focuses quite a bit on electrochemical ion insertion into a solid state host. And there's actually quite a few different applications for this type of mechanism, this fundamental mechanism of electrochemically induced ion insertion. In the present day, I think nothing captures our imagination or impacts our lives more than energy storage. And of course, the 2019 Nobel Prize in Chemistry went to the invention of the lithium-ion battery, which is based entirely upon the concept of intercalating ions at room temperature into a solid state host. This is also the technology that gives rise to electrochromics. So the fact that many solid state hosts will undergo color changes due to the electrochemical intercalation reaction. But in the coming years, this is of course my prediction entirely, there are a number of new technologies or new potential applications coming online. This includes things like ion separation and recovery of elements, so the removal of contaminants in water or the removal of precious elements in water. It includes things like ion-based electronics, where you again use the fact that oftentimes host materials undergo property changes, including in their electronics, due to the presence of the ion, as well as the fact that these materials could be used as very tunable reducing or oxidizing agents through the electrochemical intercalation process. So these are all things that we're excited about, and I'm going to share with you materials that could be used for a variety of applications, but what we're really interested in is that fundamental mechanism. So I'm sure we have a variety of different expertise areas in the call this evening. And so I wanted to share with you what we mean when we say electrochemical ion insertion into a solid state host. So typically what we talk about is that we have some insertion material that's attached to a metallic conductor that makes sure that our material is connected to an external circuit. And we oftentimes have a liquid electrolyte, though these days there's also a lot of excitement about solid electrolytes. In a liquid electrolyte, this process of electrochemical ion insertion is understood to go through several steps. So first, the cation, which is the most commonly studied species, is solvated in the liquid. It comes to this electrochemical interface where it undergoes partial desolvation. There's also some surface diffusion that has to take place for it to find an appropriate intercalation site. The charge transfer event happens where an electron is injected into the material, so that's why this is often called a double injection process. And then at this stage, there's also remaining loss of solvent, and typically what we talk about is a cation that inserts without its solvation shell into the solid host. When this process occurs, it typically, we can measure it as a current because of the electrons that are passed, and it can lead to changes in the host properties. So these could be electronic changes, these can be optical changes, and here's an illustration of a very classic insertion material, tungsten oxide. When it's electrochemically reduced through an insertion process, it turns dark blue, goes to structural and mechanical changes. All of these other responses can be used for operando and in situ techniques to correlate the electrochemical current with the electrochemical mechanism that takes place that looks something like this. Of course, this is a very simplified version of the process. I'm not illustrating here the role of the electric double layer, for example, or any solid electrolyte interphase layers that are present oftentimes, but this is kind of the basic process that occurs. And so what we're interested in our group, a lot of our projects focus on kinetics and in pushing materials that undergo insertion reactions to very high rates. And the big picture for this is that the kinetics of an electrochemical ion insertion process has very practical implications for our daily lives. Maybe back in the days when we were all traveling a lot and away from home, we would always have to wait for our technologies to charge. And so any opportunity to speed this up would be beneficial across a wide range of intercalation-based technologies. There's different ways that we can think about how kinetics manifest themselves in an electrochemical energy storage process. This is a recent conceptualization that we published in Chemical Reviews, where we kind of transformed the typical Ragone plot, which is energy and power, to something that focuses more on the electrode properties like capacity and rate or degree of structural change or overpotential. So if we look at this kind of modified Ragone plot, where on the y-axis this would be the capacity, on the x-axis this is the rate of the kinetics. We have processes like the electric double layer formation, which is very fast. It involves only electrostatics. There's no charge transfer taking place. There's no structural changes that take place. And so this is very fast, very reversible, but relatively low amounts of charge that are stored. On the other hand, you have processes that are more classic battery processes like lead acid batteries and so forth, where you have conversion or alloying. You have significant mass transfer taking place, one phase turning into another phase. These processes take much longer, but they have the benefit of having very high theoretical capacities. Insertion type processes are much faster. They typically have lower capacities. And then we have this kind of bridge, I would say, between classic insertion reactions like the tungsten oxide that I just showed and the electrical double layer reactions. We have a series of different types of surface processes that are accompanied by charge transfer taking place. These are oftentimes seen with nanostructured materials or materials that are highly porous and confine fluids. And it kind of sets up a landscape that is kind of fluid, I would say, in today's device applications world of electrochemical capacitors and rechargeable batteries. And the kinds of materials that we're really looking at in my group kind of fall within this realm of solid solution intercalation and surface redox. So overview of this seminar, I told in the title, we're going to talk about confinement. And specifically what we're going to be confining here, what I'll focus on is the introduction of water into the confined interlayer of materials and how that modifies the electrochemical environment. From an application standpoint, it's a pathway to high power electrochemical ion insertion. And kind of in a bigger picture on the synthesis standpoint, if we start thinking about the interlayer as a chemically tunable space, it's a pathway to novel hybrid materials with electrochemically tunable properties. And there's three stories that I'm going to share with you. The first is what happens when the water networks that are present, these layers, are very ordered and confined in crystalline metal oxide hydrates. The second is how we can use the displacement of interlayer ions by water to design metastable hydrated oxides. And the third is how disordered and confined water networks leads to electrochemical capacitance under confinement. So the intercalation process looks very different when you have disordered and confined water networks present. So a few years ago, I co-authored this perspective that hypothesized about what we could obtain if we functionalized the interlayer for high power energy storage. And the idea was that the classic intercalation materials, like the ones used in lithium-ion batteries, are micron scale layered materials that exhibit very high volumetric capacities, but can have slow transport processes at high rates. If we're talking about minute time scales, they can undergo fracture if there's phase transformations taking place that don't lead to homogenation of stress. As a field, we've taken materials like this, for example, graphite, and exfoliated them to make two-dimensional materials like graphene. And their studies have shown that now, because you have essentially the entire surface that can be exposed at your electrochemical interface, you don't have to worry about transport processes. You're not limited by any solid state diffusion. Any sort of volume expansion that takes place is easy because you have plenty of space. But there are downsides. For example, there's also enhanced parasitic reactions, and the excess porosity means you have low volumetric capacity. In between these two extremes are materials that could be considered kind of right, in the middle, and perhaps would combine the best of both worlds. And it turns out that relatively little has been done to understand the structure, the dynamics, and the electrochemical mechanisms in such materials. And this has been the focus of what we're doing in our group. And so the first story on the ordered and confined water networks was kind of a natural place to start, because we wanted to work with materials where the water or whatever was confined, where the crystalline structure was already known. And so we picked as our model material these crystalline tungsten oxide hydrates that you can precipitate from acid solutions at room temperature, form what are also called tungstic acids. The most hydrated form is a layered structure. You have corner sharing octahedra. Tungsten is sitting in the middle of these purple octahedra, surrounded by oxygens as well as water. It's a layered structure, the most hydrated one, about 7 angstroms interlayer spacing. There's both this lattice water that's hydrogen bonded within the layers, and very uniquely, you also have a water of coordination in this oxide, and that is a slightly longer bond in this octahedra, which explains why you have this significant asymmetry in the structure in these tungsten oxygen bonds. If you take this material and heat it up at 120 degrees Celsius, you will go through a structural phase transition, so it's very well defined, the loss of that lattice water. And then if you go to an even higher temperature that's required to remove this water of coordination, you will form the anhydrous tungsten oxide, also through a phase transition. So these are very well, all the crystalline structures for these three materials have been solved. Also, for all these materials, they contain tungsten in the 6+ state, and the tungsten is redox active, so it can go undergo electrochemical charge transfer with a variety of ions. But I'll focus specifically on here in this presentation is the insertion of protons, because we thought there could be interesting interactions between protons and these confined water networks. So that was our hypothesis starting out. Here's a little bit about the morphology and structure of these materials. If we synthesize it using the acid precipitation route, we get these platelets. The dehydration process does not change the morphology, does not really change the surface area. So this is important when we look for structure-property relationships, since electrochemical kinetics will always be affected by the surface area. One of the things that's really important when working with hydrated materials is to consider their vacuum stability in addition to the thermal stability. So we did cryo-TEM of this material and it had to be cryo-TEM in order to see this interlayer spacing. If we did it under regular conditions without the cryo cooling, regular TEM conditions, this material starts to transform into the anhydrous oxide. So this is just an important part of doing the characterization in high vacuum environments. We can also use things like Raman spectroscopy to identify the phase. So these are really beautiful structures, very model systems to work with. And the presence of the coordinated water is detected through a particularly short tungsten oxygen stretch. That's the tungsten oxygen stretch that's located directly opposite of the coordinated water. Again, these materials are kind of hybrids, right? They contain inorganic phase, the tungsten oxide, but then they also contain water. So the techniques that are really useful for these materials include things that are more often found in the polymer field. And that includes things like elastic and quasi-elastic neutron scattering. We did these experiments at Oak Ridge National Laboratory with our collaborator, Eugene Mamontov and Naresh Asti. And what these results told us was that the structural water in these crystalline hydrates is highly confined. The results were useful in telling us that the amount of water in each structure scales with, the elastic intensity scales with the amount of water in the structure. So our structure was correct as we predicted. We also found that when we looked at the quasi-elastic neutron scattering, so very small energy transfer between our sample and the neutrons, there was the water population mostly independent of temperature and scattering vector. So what that meant was that the water that's confined in these layers has no translational motion. So that's what we mean when we say highly confined. It has no translational motion. We couldn't measure any diffusion coefficient of those water molecules. So now let's talk about the electrochemical behavior, because this is where things get really interesting, at least for us. We observed the same type of phenomena in the larger scale particles, but I want to show you in particular the results we obtained from electrodeposited thin film. So this is hydrate thin film, this is the anhydrous thin film. We make these via electrodeposition, very similar surface area and morphology. This is electrochemistry or cyclic voltammetry results of the 3 different phases of this material. I'm not showing the monohydrate in the SCM, but it looks the same. And we're cycling this in a protic electrolyte and sulfuric acid. What's remarkable here, what I hope you'll appreciate, is that we're cycling this at 2000 millivolts per second, which is a charge and discharge time of less than 1 second, which is incredibly fast for transition metal oxides. It's an incredibly fast switching time. What we observe is when the current's negative, that's due to proton insertion. When the current's positive, that's due to proton deinsertion. And what we see here is first the area that's bounded by these different curves is different, and so that has an impact on the capacity, as I'll show in a second. But the other thing is that the reversibility of the electrochemical insertion process, meaning the potential separation between the insertion and the deinsertion, is much, much less in the hydrated material than in the anhydrous material, which is starting to look more and more tilted. We say that it's starting to look more and more resistive. And so here's that capacity, the area that's essentially in the curves, showing much higher specific capacity for a hydrated samples than the anhydrous sample, even though theoretically the anhydrous oxide, because it doesn't contain water, should have the higher specific capacity. So at slow enough rates, this anhydrous tungsten oxide has a higher specific capacity. So we see a kinetic difference, and it's stemming not from a surface area effect, but stemming from the structural differences in the materials. And so our initial hypothesis was that, of course, the protons must be moving through the hydrated interlayer. So we did ex situ X-ray diffraction of the proton insertion in the anhydrous tungsten oxide, and this shows what's well known in the literature, that the material undergoes phase transitions with proton insertion. So here we have a cyclic voltammogram. We're taking an X-ray diffraction pattern at these different points during the proton insertion and then the proton deinsertion. And we see there's a discrete phase transition that takes place right around this region here that's associated with the redox peak. The structure goes from monoclinic to tetragonal, and that's as we expected. What we didn't expect is what we observed for the hydrated tungsten oxide. And so this is a cyclic voltammogram of one of the larger, the platelet-like material that I showed at the beginning. We used those materials for the structural studies because we wanted to have very crystalline materials. What we observed there is that this material also undergoes a phase transition with proton insertion that's tied to these two peaks in the cyclic voltammogram. And what was very surprising is that this first peak here is completely immobile. It never changes. There's no change at all with the proton insertion or deinsertion. And this was surprising to us because if we expected a proton to be bonding at a terminal oxygen, we would expect to see changes in the tungsten oxygen bond lengths in that same, along that axis. So the fact that we didn't see that was really surprising to us at the beginning. The other thing that we did was we actually did ex situ inelastic neutron scattering, also at Oak Ridge National Lab. And this is a technique that's wonderful for studying the location of protons and being able to verify with density functional theory. And what we found from these results is that the protons go to bridging oxygens in the hydrated materials. So for example, this is an inelastic neutron scattering result. The pristine material before electrochemical proton insertion is in black. In red, the primary difference after proton insertion are in these two regions here. So a new peak and then a shift of this mode that we assigned to the OH stretching. And our collaborators at UC Riverside did ab initio molecular dynamics, and they found that these exact features that we see are due to the presence of a proton at these bridging oxygen sites that are actually located within the layers of the tungsten octahedra and not in the water networks. And so we were really curious then what was going on, because this is actually a very similar local environment as what you obtain for anhydrous tungsten oxide. So then this is of course not how the research went, but this is how I'm presenting this story. We were doing experiments, AFM experiments at Oak Ridge National Lab as well. And this is kind of an aside to say that, you know, anytime you have an electrochemical charge transfer event, you're going to have bond length changes. So even something simple as ferrocene being oxidized to ferrocenium, there's a lengthening of the iron-carbon bonds. You can use that as a feature of a charge transfer event taking place, let's say. It's the same true as in an insertion electrode. You have these coupled ion and electron process. Typically, the materials will expand. Sometimes they contract. Very, very rarely do they not experience a volume change at all. And so if you can measure the rate of that mechanical deformation, that can give you additional understanding of electrochemical kinetics. So we did operando AFM at Oak Ridge National Lab with Nina Balke's team. This is an in situ AFM cell, so this is how it looks. Our electrochemistry looks very similar as before, so more reversible cyclic voltammograms for the hydrous material, less reversible for the anhydrous material. We measured the electrochemical current in this experiment from the entire electrode that's sitting here, but the AFM response that we measure is coming just from a very local measurement of the deformation or the deflection of the AFM tip in a position where we land on top of our electrode. So this is what the surfaces of our electrodes look like. So they're similar, these platelets, there's just platelets and some polymer binder there. There was no carbon. And then sulfuric acid flooded throughout. This experiment was really interesting because it's actually how we got to this first clue that the structural change was a big difference between the two materials. For the hydrated material, we saw that its deformation for the same thickness was always less than the anhydrous material, and that there was essentially no hysteresis in this deformation for the hydrous material as there was for the anhydrous one. And anytime you see a hysteresis for any type of material's property, it is indicative of the fact that the forward and the reverse paths are they're not the same. But that was the case in the hydrous material. So same redox, tungsten 5+, 6+, but very different mechanical response. There was also very little dependence of the deformation on the scan rate, whereas in the anhydrous material, we saw that at the higher scan rates, at the slower scan rates where we had higher capacity, we had more deformation and then it decreased. And the better kinetics in the hydrous material meant the capacity was fairly constant and so was the deformation. So this was a very close relationship actually between the electrochemistry and the very local mechanical response that we were measuring from AFM. This was a really cool correlation that we found between the current, which you can think of as the rate of the capacity, and the deformation rate that we were measuring from the AFM. The correlation is so close actually that we started to call this result the mechanical CV. The dashed lines here are cyclic voltammograms. So that's measured through the entire electrode in the in situ cell. That's on this axis. These solid lines with the error bars, that's the deformation of the AFM tip over multiple cycles, the deformation rate. And you can see that it almost perfectly matches, qualitatively matches our electrochemical current for both of the materials. The places where you don't see a good match at these potential extremes is due to the onset of the hydrogen evolution reaction in the electrochemical current, which is not resulting in any volume change of our insertion electrode, and so we just don't measure anything with the AFM tip. So it's highly sensitive to the insertion process. We think this is a really interesting technique to apply for something like single particle electrochemistry and measurement of local nanoscale deformation if you're interested in the heterogeneity of the deformation across the surface of an electrode. So this was our clue that mechanics or structural changes were different between the two materials, something that we weren't able to capture the dynamics of that process using ex situ X-ray diffraction. So we turned to operando X-ray diffraction. This was in collaboration with Mike Tony's group, who's now at Colorado. And these results, when I show the figures, they always look kind of complex. So I'll walk you through them before I give you the main message. But we're doing cyclic voltammetry again. The first result is at 10 millivolts per second. And over here is our input is this linear potential sweep that's reversed. That's the 10 millivolts per second. The blue curve, that's the current response from the material. And what's shown here is the X-ray diffraction pattern, kind of looking down. So you're looking down at the X-ray diffraction peaks. This is the interlayer spacing. And these are these two other peaks that before we saw changing in the ex situ X-ray diffraction, but not their dynamics. On the right-hand side is the anhydrous tungsten oxide material. So what we see for the hydrous material is this beautiful reversible phase transition that's taking place, this doublet to singlet, doublet to singlet. And again, no interlayer spacing change whatsoever. This material is pretty constant. The anhydrous tungsten oxide at this scan rate never completely transformed. There's always two phases present when it goes through that first redox peak. So that's really interesting, is that it's never cleanly transforms the way the hydrous material does. If we push our electrodes to go 10 times faster, we see that the hydrous material is still able to keep up, goes through this transition. The time scale of it is much shorter now because we're going at a faster rate, whereas the anhydrous material is essentially frozen. It's stuck, not able to respond at all at these scan rates. So what we found from this story is that these ordered and confined water networks, we think their whole, what they're doing in the materials is that they're providing structural stability during the electrochemical redox process. We know that the inserted protons prefer the bridging oxygen sites. So those sites are located here, or if you're looking top down on the material, they're located here. The phase transformation is very, very quick in this material, and the interlayer spacing, so there's no changes measured in this dimension here. This water layer appears to be hydrogen bonded, very stable. Whereas for the anhydrous material, because you have these interconnected octahedra, we think that as a result, there's too many degrees of freedom, if you will, for structural transformation. And so as a result, you just have much more structural changes that are taking place for each electron that's injected. So the structural water in these crystalline hydrates does not seem to provide a proton conducting pathway, which was our original hypothesis, but does stabilize the structure during the electrochemical reaction. So at this point, I just wanted to stop for a second and see if there's any questions on what I've presented thus far. You can also feel free to type into the chat. Okay, if not, I'll keep going. The next story is on using the displacement of interlayer ions by water to design metastable hydrated oxides. And this is work that's been carried out by Simon Fleischman, a postdoctoral fellow in our group. So the idea here was, for the sake of applications now, tungsten's a very heavy transition metal. Our specific capacities were quite low. And so we wanted to look for something that involved a third row transition metal, preferably one that's abundant and could give us high theoretical specific capacity. So we started to zoom in on these sodium titanates that can undergo proton exchange to form hydrogen titanates. So now we're not talking about water molecules in the interlayer, but what we called structural protons. So the exchange of the sodiums by protons forms the hydrogen titanates. And one thing to note is that when it comes to proton insertion in TiO2, that's limited to the surface. So you need to nanostructure the material significantly to see any sort of significant capacity for proton insertion. The bulk protonation is unfavorable from a structural standpoint. So the nice thing about these titanates is that you start with the most protonated version of the material, the one that goes directly from the sodium titanate to the hydrogen titanate, and then you can go again through a series of structural transitions during dehydration process, where what you remove is actually both hydrogens and oxygens, and so both protons and oxygens. And these structures become more and more dense as you remove water, so that the final material is TiO2b. All of these materials are fairly large particles, micron scale particles. These are not nanostructured materials. Again, we did the elastic and quasi-elastic neutron scattering, which told us that those interlayer protons were present as we would expect. So the intensity, elastic intensity increased with proton content. We saw some interesting effects of the synthesis that suggested water was getting trapped in pores during the dehydration process. And then we also found that there was no translational motion of the interlayer protons that were present. Now for the electrochemistry, when we started with the most high temperature phase, when we cycled that in an acidic electrolyte, we saw essentially no charge storage process taking place. We start to add more interlayer protons, go to a lower temperature, still nothing. Then we start to see the presence of something that looks like maybe some electron transfer taking place, but the specific current was fairly low. But in the case of the most protonated material, we saw the most significant specific currents. So the proton insertion, significant proton insertion, seemed to only occur for the H2Ti307 phase, the most highly protonated phase. This process, one of the downsides is that the reduction potential is pretty low. So we always had to go to very fast cyclic voltammetry scan rates to avoid the competition with the hydrogen evolution at low scan rates. This was the deprotonation capacity. So to avoid counting the HER current in our capacity, we only considered the deprotonation or the anodic capacity here as a function of scan rate. And we saw that we could obtain up to 80 milliamp hours per gram in these micron scale materials, which is about 0.4 hydrogens per titanium. And we saw this very strong correlation between the interlayer structure, the interlayer environment, and the charge storage capacity, with fairly good rate capability, I would say, even for these micron scale particles. We did in situ Raman spectroscopy, and it showed us that there's reversible structural changes that are taking place as a function of the applied potential, as well as a very strong blue electrochromism. All of these are indicative of a bulk insertion process taking place into the materials. To help us understand, in this case, why we saw this very strong dependence on the degree of structural protonation, we turned to density functional theory through our collaborators at UC Riverside and found that in the H2Ti307, the absorption energy for electrochemically inserted protons is fairly low, and it's accompanied by an interlayer contraction. That's how the structure accommodates the excess protons. On the other hand, if we compared those absorption energies to the next structure, those absorption energies increased, almost doubled, more than doubled, and that required, that was associated with a more significant distortion that had to take place to accommodate the protons. So this was another example now through metastable synthesis, soft chemistry routes, to favorably tune the interlayer environment to enable bulk proton insertion in the hydrogen titanates. Along these lines, we also started a project to look at sodium ion insertion in aqueous electrolytes. This type of process is of interest for very low cost energy storage as well as for electrochemical desalination. And so there's some things that I want to point out that are quite unique when you do insertion chemistry in aqueous electrolytes. In the case of non-aqueous electrolytes, you kind of always almost assume that your cation is moving into the material in a desolvated state, that you have to maybe pass through a solid electrolyte interface layer, but there is some, there's basically the ion and then desolvated energies are lower in non-aqueous electrolytes. On the other hand, in aqueous electrolytes, you don't have the SEI formation. The hydration energies are much higher, especially for ions like lithium or sodium. And so now you have to consider the solvent, water, as taking part in the intercalation process. And so in particular, we were interested in looking at these very well-known layered sodium metal oxides called the P2 oxides. They're called P2 because the sodium is in a prismatic site and the oxygen stacking sequence is this ABBA sequence. The structure is quite flexible to accommodating different transition metals in what's called the transition metal region. You could have, we chose manganese-rich compositions and then varied what the other dopants were. In the electrochemistry, the aqueous sodium ion intercalation electrochemistry was quite different actually, depending on what that dopant would be. So for example, we had this composition that had manganese as well as a little bit of nickel and copper. And the first and second cycle, you saw pretty much, I mean, there was capacity decrease, but the same peaks were present for the first and the second cycle. On the other hand, if we took the same material but now replaced the copper with iron, we saw less pronounced peaks during the first sodium deinsertion process. And after that, those peaks disappeared. There was essentially almost no potential dependence of this material, which looks like and which we consider to be a capacitive behavior now. So we looked at some other compositions. We did scanning, tunneling, electron microscopy of the materials. Even some of them became very reactive just due to the exposure of water, which is pretty well known. And so it was kind of driving the point that the transition metal content was dictating what the interlayer environment would be. And so what we observed, we did some operando X-ray diffraction. This is now the in situ cyclic voltammogram showing, again, we have this first cycle where there's clear peaks in the cyclic voltammogram, but they disappear on subsequent cycles. What we obtained from the operando X-ray diffraction is that this is the first sodium deinsertion cycle of the P2 phase. There is a very discrete stage upon the deinsertion of sodium ions where the structure transitions from the P2 phase to a hydrated phase that we called Bernesite-like, meaning that water molecules were now present in the interlayer. And then this Bernesite-like, this hydrated interlayer phase, was electrochemically active on subsequent cycles. It would cycle sodium ions in and out with expansion of the interlayer during contraction of the interlayer during sodium insertion, expansion during deinsertion. However, during this transition here, there's a 25% C-axis change that leads to very significant microscopic exfoliation and essentially failure of the electrode. So now I'll talk about the last part of the presentation, where we take this disappointing result, if you will, or electrodes failing, and observing something very interesting that tells us about electrochemical capacitance under confinement. So I just showed you the story. We take the P2 oxides, we remove sodium from the material by applying potential. At some critical desodiation level, water comes in from the electrolyte we believe to offset the repulsion between these layers, and you get this bernicite-like phase. Bernicite is a well-known material in the electrochemical capacitor community, but when this process occurs on the electrode, this volume change results in electrode failure. So we came up with a kind of a bulk electrochemical expansion process. We took the P2 oxides, put them into this pouch cell that was made from dialysis tubing, so nothing fancy, applied a very high voltage between this and a counter electrode to drive out as much sodium as we could. And what we get out of that is an expanded and hydrated material. But now it's all a powder that we can assemble into electrodes. And if you go back to one of the earliest slides of my presentation, where I said, wouldn't it be nice to investigate the materials in between the bulk and the complete exfoliation? This is essentially that material. And what's really interesting is that now we do the cyclic voltammetry of these materials. We know from the operando X-ray diffraction results that this is due to sodium insertion and deinsertion into a hydrated interlayer, and it looks almost like a perfect capacitor. The electrode integrity is much better. We can cycle these for thousands of cycles. The structure is stable, and we can compare it to activated carbon, and we observe at very fast timescales essentially the same performance, suggesting that we're really limited by the electrode architecture. And at slower timescales, we actually see better volumetric capacitance. And the surprising thing is that we're taking a material that has a surface area of about 1 meter squared per gram, which is what we expect from the high temperature synthesis, and comparing it to activated carbon that's synthesized with a surface area of over 2,000 meters squared per gram. So we think that the expansion and interlayer hydration is what leads to the capacitive ion intercalation in now this micron scale bernicite material. So you don't have to actually exfoliate the material completely to access a high surface area response, because now you have this confined and hydrated interlayer. So now I've reached kind of the conclusion of my presentation. I shared with you the role of water in the interlayer in these very tight environments and how it affects charge storage in different classes of transition metal oxides. Where we're going with this, and what I kind of coined, maybe is not a particularly funny catchphrase, but there's plenty of room in confinement. I think there's a lot of really interesting electrochemical phenomena to discover, and that includes electrochemical reactivity. So instead of looking at just things like alkali ion or proton insertion for energy storage processes, we can also start to look at things like electrochemical reactions under confinement, because the things that happen under confinement is that we can start changing the physical and absorption properties of whatever's confined in this interlayer region. And layered materials are actually very ubiquitous in theoretical studies of what happens during confinement. And I think we're at the stage where now the synthetic prowess is there to start really making those theoretical predictions to validating them with experimental predictions. And I have a perspective on this topic with my group members in the recent issue of Chemistry of Materials. So in conclusion, I think that there's a lot of very interesting science and applications to be done when we start to blur the distinction between a liquid and a solid. I've presented some ideas for what we can do in the realm of energy storage. And then I think going forward in electrochemical reactivity, that would be the next frontier to tackle. And again, I'd like to thank my research team, my students and postdoctoral fellows, our collaborators, as well as our funding agencies for their support. And thank you all for your attention to my presentation. I'm happy to take any questions you may have.
Hello, Vero. I think that there are some questions from the chat box.
Okay. Let me see if I can pull that easily. Okay. Oh, great. So it's one of Mike Tony's students. There's no structural, if there's no phase transition upon protonation, would the structural expansion layered oxides be detected by high resolution X-ray scattering? So we do, I'm trying to think, we haven't seen, we haven't really seen a solid solution type process, at least not in the tungsten oxide hydrates. And the titanates, we're not sure. We only did a couple of ex situ experiments. But even though the protons are essentially point charges with no mass, they do have a significant, their charge does have a significant influence on metal oxygen bond distances. So I think you will see something in X-ray scattering results. And the surface protonation in TiOX, so in TiO2, if it's due to a kinetic effect, it's due to the fact that you have it's difficult for the protons to insert into the bulk structure. There's no favorable sites, so they prefer to sit at the outer edges. So I think there's some other questions there that maybe we can talk offline about protonation and deprotonation and electrocatalysis is quite an interesting topic. There's a lot of interesting work going on with that right now. Batteries in aqueous solutions, there's actually no commercialized proton insertion and deinsertion battery. That's a little harder to answer. And as far as whether the protons inserts by itself or with a solvation shell, for the materials that I've discussed here, the ones where we're talking about proton insertion, it seems to be just a proton, so not a hydronium ion. I hope that covered most of what you were asking. These are a lot of really good questions.